Hey guys, welcome to this new video. We want to discuss some example of the Laplace transform, as we mentioned when I introduced the concept of the Laplace transform. So here we focus on solve few examples, and this is the first example. I want us to solve the Laplace transform of t times u. The u is a function of t minus 1, and I just wrote this. This is from the table of the Laplace transform, so that you remember that when you have this form, you'll be able to use the Laplace transform to solve this. But now this form is not really similar to what we have here. What can we do to get here? So first of all, we can see here that the argument is t minus a, and here is also t minus a, while here we only have t minus 1, and the other side we don't have t minus 1. It's not, it's not the same, right? So what can we do? We can rearrange this in the following way. If we say the Laplace transform of t times u of t minus 1 is the Laplace transform, okay, of t. If we take t, we subtract 1 and we add 1 times u plus t minus 1. Right. Here 1 plus 1 minus 1 is 0, and then we remain with t, right? So here, if I split this, we multiply with this and this, then we obtain t minus 1 plus 1. We multiply this by u of t minus 1, okay? So at this stage, we are free to expand this. If we expand, we have the following: Laplace transform of t minus 1 times u of t minus 1 plus u of t minus 1. All right, at this stage, remember the property of the Laplace transform. We say that the Laplace transform is linear. It means that the Laplace transform of this first term plus this is the Laplace transform of this term plus Laplace transform of this, okay? So linearity, Laplace transform of t minus 1, u of t minus 1, plus, we close here, plus the Laplace transform of u of t minus 1. All right, at this stage, this is pretty good, because here we have the same t minus 1, t minus 1. So the function, our function f here, we can take it as a function of t, the same argument as the functions of u, right? All right, at this stage, we apply the definition of the Laplace transform. So by definition of the Laplace transform, this is the integral from 0 to infinity, okay, of this function. This is t minus 1 times u of t minus 1 times e to the power minus st dt, plus, for the second part, it is the integral from 0 to infinity of u of t minus 1 times e to the power minus st dt. So remember that the integral from 0 to infinity of u of t minus a e to the power minus st dt is the integral from a to infinity of e to the power minus st dt. So if you apply this to our case, then we have the following. This becomes the integral from 1 to infinity, okay, t minus 1 times e to the power minus st dt, plus the integral from 1 to infinity e to the power minus st dt. I want to also make this change of variable. Let tau be t minus 1. This means that d tau is equal dt. Okay, so if you make this change of variable, then this integral become the integral from 0 to infinity, because when t is infinity, tau is also infinity, of tau e to the power minus s. T is tau plus 1 d tau plus the second part. The second part here is the integral from 0 to infinity e to the power minus s tau plus 1 d tau. All right, at this stage, we can use the integration by part to solve this, why this integral is straightforward, right? So for the first one, let's use the integration by part. Let's say f is tau and g is e to the power minus s tau plus 1. So the first derivative of this is 1, and sorry, this is g prime, and then g is minus 1 over s times e to the power minus s tau plus 1. We just have to substitute here. F times g is minus 1 over s times tau times e to the power minus s tau plus 1. Okay, this is from 0 to infinity. The second part is straightforward. The second part is this integral, the negative sign, minus minus is 1 over s, integral from 0 to infinity of e to the power minus s tau plus 1 d tau, plus the second part. The second part here is just the integral from 0 to infinity e to the power minus s tau plus 1 d tau. All right, here, if we substitute the limit when tau tends to infinity, then we see that the exponential function grow quicker than this polynomial tau. If you compare these two, you see that at infinity, this product is dominated by the exponential function, and therefore the exponential negative infinity decrease to 0, right? So this is 0, and the second limit here is also 0 because of tau. All right, so if you agree that this part is 0, then we only remain with this. This is 1 over s plus 1, the integral from 0 to infinity of e to the power minus s tau plus 1 d tau. This is straightforward. So the integrals of this is minus 1 over s times e to the power minus s tau plus 1 from 0 to infinity. Again, we substitute the limit here. This is e to the power minus infinity, that's 0. And when we substitute tau by 0, we have 1. E to the power 0 is 1. So this is 1 over s plus 1 minus 1 over s, 0 minus 1. All right, the final expression here is 1 over s, because here it is just 1 over s, right? Times 1 over s plus 1. So it is very simple. You can play with this. I can give you another example that you have to solve. All right, can you pause this video and just find the following integral? You just have to use the same techniques, okay? Find the following Laplace transform of, let's say, a u of t minus pi over 2 cos t. What is this? Basically here you just have to use the same technique, okay? Make sure that they have the same argument, and that should be all. Thank you so much.